Hello everyone, I'm Dr. Kumar and today we are going to discuss about the part 3 of electricity and magnetism. So let's begin. So in this short video we'll be discussing about basically the electromagnetic induction, Faraday's laws and Lenz laws and their applications. So before going to electromagnetic induction, so first let's talk about how does a magnetic field produced by a current carrying conductor. So magnetic field can be produced in two ways, by permanent magnets and by current carrying conductors. So magnetic field due to permanent magnets, we all know about that, but how magnetic fields generally generated due to the current carrying conductor, so we will be discussing here. So for example, suppose this is a conductor and current flowing in this direction, in the upward direction. So when current flows in this direction, a magnetic field will produced and circling or around this conductor. Either it is in clockwise direction or anti-clockwise directions. It's totally depend on the direction of the current. For example, the direction of this magnetic field you can find out by right hand rule. So for example, suppose consider this conductor and this is the direction of the current. So what you have to do, so you have to point your thumb along the direction of the current and you have to curl around the other four fingers in such a way that the direction of these fingers will give you the direction of the magnetic field produced by this current carrying conductor. So in this case, you can see this is the direction of the current. So if you view through the top, then you will find that the direction of the magnetic field is anti-clockwise direction. On the other hand, if the current flows in downward direction and if you view through the upward directions, then you will find that the magnetic field, it is in it is in clockwise direction. Now what will happen when two current carrying conductors, if we bring it closer together? So for example, these are two conductors and this is the current which is flowing in the upward direction. So in this case, these two conductors will experience a force in this direction, and so these two conductors will attract each other. So always remember that if the current which flows through the conductors are in same direction, then these two conductors will attract. On the other hand, if the current flows in opposite direction, for example, in this case you can see the current in this conductor, it is in upward direction, and the current flows in this conductor, it is in downward direction. So in this case the forces are in opposite direction. So these two conductors will repel each other. Okay, now let's talk about the electromagnetic induction. So in our last slide we have discussed about how magnetic field can be produced in two ways, that is by permanent magnet and by current carrying conductors. Similarly, current also produced by two ways. So we'll be discussing here. So for example, we know that current can be produced when we apply potential difference. So for example, in this diagram you can see that this is a battery, this is the positive terminal of the battery and this is the negative terminal of the battery, and when this electric bulb is connected to the positive and negative terminal of the battery, and this is the switch. So when this switch is closed, so we'll find that the current flows from positive terminal of the battery and it goes through this wire, through this load, that is electric bulb, and it will come back to the negative terminal of the battery. So in this simple example, we have seen that we can create or we can produce current by producing potential difference. Similarly, there is another way of producing current which is known as the electromagnetic induction. So this is very important, and This is very important in practical applications. For example, whatever we have get electricity in our household. So this is the basic principle of producing current. So let us consider this is a current carrying conductor in a circular form, and this current carrying conductor or this loop is connected to a galvanometer. And what you have to do, so you need to bring a permanent magnet towards this conducting coil so that the magnetic lines of force are passing through this circular area of this loop. So when you bring these magnets towards this conductor or conducting loop, so you will find that there is a deflection in this galvanometer. Similarly, when you take this permanent magnet away from this conducting loop, then again you will find that there is a deflection in the galvanometer, but in this case it is in opposite direction. That means when you bring this permanent magnet towards this conducting loop, suppose the deflection is in this direction, that is in right hand direction. On the other hand, when you take this magnet away from this conducting loop, then you will observe a deflection in this galvanometer in the left hand direction. Now you can ask me a question, so what will happen if I don't move these permanent magnets to and fro from this conducting loop? Then you will observe, obviously, then there will be no deflection in this galvanometer. So this is the way, that is how you can produce a current by changing the magnetic fields of lines through this conducting loop. And this is basically known as the electromagnetic induction. So electromagnetic induction is basically the production of electromagnetic force across an electrical conductor in a changing magnetic field. Therefore, when you change the magnetic field lines through the conducting loop, then there will be an electromotive force or EMF will induce in this conducting loop, and correspondingly there will be a current which is known as the induced current. But when you don't move the magnets, so there will be no change of magnetic lines of force passing through this conducting loop, and therefore there will be no induced EMF in this conducting loop, and you will not eventually get any current in this circuit. The phenomenon of electromagnetic induction was first observed by Michael Faraday and Joseph Henry simultaneously in the late 19th century. So in his attempt to produce an electric current from a magnetic field, Faraday used an apparatus like this as shown in the figure, and a coil of wire, this one suppose, was connected to a battery. The current that flowed through this coil produced a magnetic field that was intensified by the iron core. Faraday hoped that by using a strong enough battery, a steady current in this primary coil would produce a great enough magnetic field to produce a current in this secondary coil. This secondary coil is again connected to an emitter to observe whether the current is produced or not. He met no success with steady current, but the long soft effect was finally observed when Faraday saw that the emitter, which is connected to the secondary coil, deflects strongly at the moment when he closed the switch in this circuit, and the emitter deflected strongly in the opposite direction when he opened the switch. A steady current in the primary coil had produced no current in this secondary coil. Only when the current in the primary coil was starting or stopping was a current produced in the secondary coil. So Faraday concluded that although a steady magnetic field produces no current, a changing magnetic field can produce an electric current. Such current is called induced current. When the magnetic field through the secondary coil changes, a current flows as if there were a source of EMF in the circuit. So from his experiment, Faraday concluded that an induced EMF is produced by a changing magnetic field. So we know that magnetic field, like electric field, is a vector quantity, and the magnetic field can be represented by magnetic field lines of force. So magnetic flux the magnetic flux is defined as the number of lines of force passing through a surface. So for example, considering this surface whose area is, or the surface area is A, and if the magnetic field, these are the magnetic field lines of force passing through this surface, normal to this surface, and then the flux would be represented by B dot A, where B is the magnetic field and A is the surface area. Now since the magnetic field lines of force are perpendicular to the surface area, so this flux will be BA. Otherwise, if this magnetic field produces an angle with the surface area, for example, if it is theta, then the flux can be represented as BA cos theta. On the other hand, in integral calculus, so if we consider, the magnetic flux can be represented like this, where dA is a small elementary surface of surface A. So based on his experimental observations, Faraday proposed two laws, which is known as Faraday's laws of electromagnetic induction. So Faraday's first law says that if you change the magnetic flux passing through a circular or any other coils, then an induced EMF will be produced in the coil, and if the conductor circuit is closed, the current will also circulate through the circuit, and the current is called the induced current. Now the Faraday's second law says that the rate of change of magnetic flux which is passing through the circular coil is directly proportional to the induced EMF. So if J is the induced EMF, then it will be proportional to d phi dt. So from Faraday's second law, we can write J will be equal to minus n d phi dt, where this capital N is the number of turns of the coil, and phi simultaneously we can write as like this relation. Please note that there is a negative sign in this Faraday's second law, so this negative sign will be discussed in the next slide, and this negative sign is basically come from another law which is known as Lenz law. Therefore we have seen that the Faraday's second law is basically gives the value of the induced EMF, whereas Faraday's first law gives the idea about the induced EMF. So from Faraday's laws we have discussed about how induced EMF and induced current can be generated when you change the magnetic flux passing through a coil. But unfortunately Faraday's law doesn't give in which direction the EMF will be produced in the coil. So the direction of the induced EMF was given by Lenz law. So according to Lenz law, an induced electric current flows in a direction such that the current opposes the change that induced it. Now, for example, consider that you are bringing the north pole of a magnet towards this conducting coil. So when you move this magnet towards this coil, obviously the magnetic lines of force passing through the coil also changes. So due to this change, and induced EMF and simultaneously an induced current will generate in this conducting coil. Again, we have discussed that when current flows through a conductor, a magnetic field will also generate. Therefore, as long as the induced current will generate due to the changing magnetic flux, therefore this conducting coil will also generate a magnetic field. And according to Lenz law, the magnetic field produced due to this induced current is such that this will oppose the motion of this magnet or the change of original magnetic flux. Therefore, Therefore, the direction of the current in this conducting coil is such that, so this side of this coil or the conducting loop produces a north pole, so that this north pole will oppose the north pole of this bar magnet, and simultaneously the opposite side of this conducting loop, a south pole, is generated. So the lines of force because of this induced current will be like this. Now suppose in the second case you are moving this bar magnet away from this conducting loop. So according to Lenz law, when you move these bar magnets away from this conducting loop, the direction of the current is such that the magnetic field produced due to this induced current will oppose the motion of this bar magnet, or the change of magnetic flux which is passing through the conducting coil. Therefore, the direction of the current in this conducting loop is such that this time there will be a south pole will generate in the left hand side of this conducting loop, so that this south pole will attract the north pole of this bar magnet, and therefore the direction of the current and therefore the magnetic field produced by this conducting so therefore the magnetic field produced due to this induced current will oppose the motion of this bar magnet. Therefore, in this case, the lines of force of the magnetic field due to this direction of the due to the induced current will be like this. Therefore, we have seen that in both cases the direction of the induced current is opposite to each other, and these things and this direction of induced current is basically depends on how you are trying to change the magnetic flux passing through this conducting coil. Now, one thing you should always remember that it's not required to move the magnets only in order to change the magnetic flux passing through the coil. So you can move this conducting coil in front of this static bar magnet, and again there will be a change in magnetic flux, and in this case also there will be a induced current or induced EMF produced in this coil. There are several ways to change the magnetic flux actually. So you can rotate this conducting coil in front of this bar magnet, and again in this case there will be a change in magnetic flux, or you can just change the surface area of this conducting loop by suddenly increasing the loop area of this conducting coil. Now suppose let us consider that Lenz law is not true. That means the direction of the induced current is such that it doesn't oppose the motion of the bar magnets, or it does not oppose the original change of the magnetic flux which is passing through the coil. So in that situations what will happen? So let's see this. Suppose you are bringing this bar magnet towards this coil, which is again connected to a galvanometer, right? So you are the north. So in this case, the north pole is facing towards the surface of this conducting coil. Now, because of the change of magnetic flux which is passing through this conducting coil, so a current will induce in this conducting coil. And suppose imagine that in this situation, the direction of the current is such that it doesn't oppose the motion of the bar magnets or the original change of the flux which is passing through the conducting coil. So therefore, the direction of the magnetic field due to the current induced in this coil is in the same direction with the direction of the magnetic field of this bar magnet, and therefore the magnetic lines of force passing through the coil also increases, and as the magnetic flux increases through this through this conducting coil, and therefore the induced current will also increase. And as the induced current increases, again the magnetic flux passing through the conducting coil also increases. In this way, the magnetic flux increases continuously, and the current, that is induced current, is also increases continuously. And if you take out this bar magnet also, again there will be a change of magnetic flux which is passing through the conducting coil, and simultaneously current will also increases. And therefore this is a violation of the conservation of energy. Therefore, to sustain the conservation of energy, the direction of the induced current is in such a direction that it will always oppose the direction of this bar magnet or the original change of the magnetic flux which is passing through this conducting coil. Therefore, Lenz's law is always true, and if it is, or if it doesn't, or if it is not true, then there will be a serious problem in the conservation of energy. So we should always remember that Lenz's law is always true. Now let's discuss about the applications of the electromagnetic induction in science and technological field. Electromagnetic induction, the phenomena of electromagnetic induction is generally used in variety of instruments which we are using in our day-to-day life. For example, motors and generators are basically work on the principle of electromagnetic induction. The electromagnetic induction, or the phenomenon of electromagnetic induction, is applied in automobile braking system. In modern automobile or in modern cars, the braking system is basically work on the principle of electromagnetic induction, which is basically one kind of that means it is basically work on the principle of Lenz law and the eddy current. So the principle of electromagnetic induction is also applied in transformer, which is used to transport the electrical current to our houses.